Okay, welcome back, everyone. Today we're very happy to have a guest lecture by Joanne Truong. Joanne is a PhD robotics PhD student in the School of Interactive Computing. She's jointly supervised by Professor Sonia Chernova and me. Um, she's done a lot of interesting work in navigation, locomotion, and now some manipulation problems as well. She's done a lot of sim to real work. So I often think of myself as robotics light, if you will. Like I sort of sneak into that area, do a little bit of work in simulation. Joanne is true robotics. She's a roboticist in the sense that she's actually worked with hardware all the way from her undergrad to her PhD studies. What she's going to be talking about today is a continuation of the things that we've been talking about in this lecture. So it's a nice transition from on policy or policy-based reinforcement learning methods. We taught you what reinforces and what A2C is last time. Joanne will continue that discussion, but also ground it very heavily in the context of robotics and navigation problems with robots. So with that intro, take it away, Joanne.
Yeah, thanks, Drew, for the introduction, and welcome to today's lecture. Again, Drew already introduced me, but my research interests are robotics and sim-to-real transfer, and so I'll talk a bit about that today. So the lecture plan is to combine CNNs, LSTMs, and reinforcement learning all together. So these are all modules that you've learned throughout this course, and I'll introduce this through a task called point goal navigation. I'll also introduce more advanced reinforcement learning topics such as advantage actor critic, trust region policy optimization, and proximal policy optimization. And finally, I'll show results on these reinforcement learning algorithms on point goal navigation on real robots. So let's begin. So as we've seen up till now in class, there's been remarkable progress in computer vision over the past few years. And today's state-of-the-art systems are quite good at doing things like object detection, so identifying people or objects in images, and they can even segment these objects out in images. Models can also describe images with rich natural language sentences, and they can even answer questions about a given image. And so all of these advancements and all of this is possible due to large neural models trained on large static data sets that we all have access to. And so while this is great, if we think about some of the applications that we want to deploy these models in, we can imagine a scenario such as this, where there is a physical agent or a robot. This robot can potentially be in a hostile environment. So for an example, this is an image from the DARPA Robotics Challenge where the robot is sort of a first responder and it needs to go into this building. This robot can take actions and interact with the world. And this robot can potentially also have natural language interfacing capabilities to talk to humans in natural language. And so for an example, let's say there's a first responder and it's asking the robot, is there smoke in any room around you? The robot would look around and say, yes, in one room. And then from there, the human can instruct the robot further to go look for people and then so forth. And so deploying the models that we've trained in traditional internet vision paradigms is sort of incompatible with how these would be used for real robot applications. And I'll walk through some of these challenges now. So the first big problem is that the agent no longer has access to well-composed curated images. So while images from ImageNet are sort of very clear, let's say there's a dog in the photo, the dog is in the center of the photo, it's really prominent and is really well oriented in the picture. But if we have a robot in the real world, this robot would have to reason about objects, scenes, or attributes, and also have to come up with a sequence of actions to perform for some downstream task purely based on this egocentric or first-person vision. And so as you can see, as humans or robots would walk around in the environment, what they perceive can also be very bumpy or shaky, and the objects aren't well composed as they would be in these static data sets. Another key problem is that there is no longer a static data set. Instead, the agent is controlling the pixels that come through that it sees based on the actions that it performs in the environment. And so this means that the agent controls its incoming data distribution, and this data distribution would constantly change as the agent learns. And we'll see how this becomes a problem later today when we discuss some reinforcement learning algorithms. And another challenge is that unlike supervised learning, where there's an immediate error signal for every instance in a static training data set. So for instance, if you were to do object detection, you would feed the image through some CNN, you would get a prediction for that, and then you would be able to calculate loss from your static data set and then backprop this. Now you don't have access to this, where if you were to train an agent, the agent might be performing a long sequence of hundreds of steps only to see a single scalar reward at the end. And based on this reward, it'll have to decide which of these actions led to that outcome and which actions it should change in future iterations to do better. And lastly, another key challenge that we'd want to overcome is that we'd want to be able to teach these agents to do some language understanding capabilities in order to actually talk to humans. And so how can we transition from this world of internet AI, where models are trained on static data sets, into what we call embodied AI, where the embodied agent needs to take actions in its environment? And so one way to train these agents is to do it directly in the real world. However, training robots in the real world is slow. So the real world can run no faster than real time, and it can't be parallelized. It can be dangerous, so poorly trained agents can injure themselves or the environment or others around them. It's resource intensive, so the robot and the environments that they're in demand resources and time. So in the video on the top, this is a video from Google Robotics, and so they built this whole rig in order to have the robot learn in the real world on their own, but they had to spend many months sort of developing the system that would tether the robot and be able to reset the robot if anything bad happened. So this is only possible because Google is such a large research institution. In the bottom video, you see there's a human that's supervising this robot constantly. The human would have to step in sometimes to maybe charge the robot's battery or to fix it if anything goes bad. So this is also very resource intensive. And it's also not easily reproducible. So replicating conditions across experiments or institutions is hard. So if I were to run an experiment here at Georgia Tech and then someone else is trying to run the policy in California, and there are windows in the room, if the lighting changes, the outcome of the policy might also be affected. So an alternative approach is to train embodied agents in rich realistic simulators and then transfer these learned skills to reality. So here is an example of some 3D data sets that can be used within a simulator, and these are all photorealistic scans of real-world household environments. And highly photorealistic simulators allow us to study complex tasks such as point goal navigation, object navigation, and room navigation, among others. Simulators can run orders of magnitude faster than real time, they can be highly parallelized, and they can enable decades of robot experience be collected in days. So the simulator I just showed was the Habitat simulator, and this was created by a large team of researchers across many different institutions. And so if you started homework 5, this might look a bit familiar, as this year's assignment uses Habitat for training a fetch robot to reach a certain point in the environment. So let's go into the details of Habitat a bit more. So the core idea of Habitat was to standardize the embodied AI software stack. And so to do this, they started at the lowest level. So the team looked into the variety of data sets of 3D environments that existing works have been using. Next, they look into existing simulators and the capabilities of these simulators, such as focusing on rendering, physics backends, support for a variety of different agents, or support for human input. And at the highest level, we have the tasks that have been defined on top of these existing simulation platforms that researchers are interested in investigating. So an example of a task would be embodied question answering. So in this example, a human asks what color is the car. The embodied agent would have to take actions in the environment. So here it goes outside to the garage, sees the car is orange, and answers the question that the human asked. Another example task is vision and language navigation. So here the agent is given a natural language instruction, and the robot would have to follow these instructions in order to get to the final location that it wanted to go to. So in this example, the instruction was leave the bedroom and enter the kitchen, walk forward and take a left at the couch, and so on. And so the Habitat platform incorporates all of these layers into a general flexible platform that allows users to use any data set they want to in the simulator. They developed Habitat Sim as a simulator, which is very highly efficient. And finally, there's Habitat Lab, which is the high-level library for the development of embodied AI agents. So that's sort of the API interface for training these agents. And now I'd like to transition into two demos. The first one will be Habitat on Web, where we're actually running Habitat on the web. This was made by one of your peers, Ram, and he was using this for one of his research projects in the lab. So let me start this. This is an example of object goal navigation. So this is a task demo, and then there is a training task. So here, the task is to find and go to the fireplace. So as the human, I can use the W key to move forward. I can turn around with my arrow keys, and now I'm looking for a fireplace. So if I were to mistakenly say that this is a fireplace and I click submit, then it should tell me that I'm not within 1 meter of the object. So therefore, I need to continue looking for the fireplace.
And just to add to Joanne's comments here, this feels almost like an online video game, if you will. And the concepts, the underlying graphics concepts are fairly similar. There's a renderer that's running in the browser, and the user keys are being used to move this virtual robot, if you will. And this is something that can be connected to a task like Amazon Mechanical Turk, where you can ask, Mechanical Turk workers to control a virtual robot, and you can get these things called expert demonstrations or human demonstrations for this task.
Yep, and so I think I found the fireplace, so I'll click submit, and then hopefully it'll accept my answer. And then, so this is what the Mechanical Turker would see, and so they would have completed this task. Yeah, and I'll also show a demo of running Habitat Sim locally. So this also runs locally on my Mac. I'll make this bigger, but I still want to see the key commands on the side. So here I am an agent in this house. So this is sort of an orthographic view of the house. But if I were to be back as an agent, I can walk around in this environment. I can collide against these furniture objects. So these are all static in the environment, and so I'm sort of colliding with the objects here. You can also add interactive or objects that sort of obey physics here. And with the mouse, you can also click and move these objects around, and they would fall down due to gravity. So the agent can be at a configurable height, and the agent has access to a bunch of actions that you can take in the environment. Sounds good. Go back to the presentation now.
Yep, thanks, Joanne.
Yep. Yeah, so now that we've introduced the simulator, I'd like to introduce a common task that people train agents for. So first, let's introduce point goal navigation.
Right.
So in this task,
Actually, there's a question that has come in that might be appropriate to get at this point because it'll keep coming in future visualizations as well. Why are there sometimes gaps in the frames? I think they mean the holes in the reconstruction. And at some places there are blurry spots that the texture seems blurry. So I can answer that question, or you can take a shot, Joanne.
Yeah, I'll give my best explanation. You can correct me if there's anything I'm missing. So these are scans of real-world environments, and so how you would do that, I have a video of this later on, but you have
Joanne,
a 3D. Yeah.
actually, would you mind pulling up the demo again so you can point to one of the holes? That way, everybody else in the class will also see what we're talking about.
Yep. Um,
Yeah, like right there on the left, there were some holes. Go turn left again. Yeah, there
Oh,
on the
yeah.
window.
So the holes. Yeah, so these are scans of real-world environments. And so when you place these scanners, there might be reconstruction holes, mainly in windows where it's sort of transparent. And then I think the blurs on the ground are where the camera was placed because it can't necessarily capture the space directly below it, although I can't find the blurs right now. So these are small artifacts just in the reconstruction of this 3D environment.
Yeah. And so Joanne will show a video later in her slides where these things are constructed by taking panoramic RGBD observations from this environment. If you've taken a computer vision class, you will study 3D reconstruction and more specifically multi-view geometry, where you try to solve a correspondence problem and then estimate the depth of every point, and then that gives you a point cloud of the 3D environment. All of that is being solved here, and any errors in the underlying reconstruction are what are showing up as holes in these meshes. So the entire world, according to the simulator, is a gigantic 3D mesh comprised of triangles with textures of triangles. So the holes are actually missing triangles. There's just pure geometry that's missing there, and the blur that was observed in a different environment is just lack of capture of those pixels from one of the camera observations. So that's not something that a simulator can fix. That is something that modern neural network algorithms can solve via in-painting and hallucination. But we'll hold off on discussing that till we get to VAEs and GANs. Go ahead, John.
Yep. Let me share my slides again. Yeah, so the task of point goal navigation. So in this task, a robot is spawned in a previously unseen environment at some start location, and it has to navigate to a goal location, but it doesn't have access to a map at all. So this top-down map is only for our visualization purposes, but the robot doesn't have access to this. The robot has access to an egocentric depth camera, an RGB camera, and also a GPS and compass sensor that it uses for localization, and this tells it how far away it is relative to the goal. So here is an example of the agent completing this task. So it's walking down the hallway, and then it reaches the goal, and then it can call stop. So the agent that's used for this, the robot is called Localbot, and this is what it looks like in simulation. So this is just a replica of the real-world robot that we have on campus. And so this robot is 0.6 meters tall. Essentially, it's just a cylinder, and it's 0.2 meters radius. And so the robot has access to a set of discrete actions. So one action is the stop action. So the agent would use this action to indicate that it believes it's completed the task. So once it gets within 0.2 meters of the goal radius, it has to indicate that using the stop action that it believes it completed the task. The robot can also call the forward action to move 0.25 meters forward, and it can also turn left or right 30 degrees. If the agents were to be initialized in a previously unseen environment, it would get in a camera observation. So we're just using RGB here to illustrate this point. It'll also get the GPS and compass sensor. The RGB images are fed into a ResNet 50 visual encoder, and the GPS and compass is embedded, and both of these are concatenated and used as input into a policy. So here our policy is a 2-layer LSTM network, and this is used to directly predict what action the agent should take at a certain step. And at every time step, the hidden state from the previous time step is fed into the current policy. The image observation updates as the agent takes actions, and the agent would sort of unroll this out into a sequence of actions for it to take until finally it calls stop when it thinks it's reached the goal.
And so just to add here, can you go back to the previous slide? So this slide really is an example of everything that you've learned in this class coming together. The images are being encoded through a CNN, so everything that we've learned in that module applies. The policy pi theta is a recurrent policy, and so that's building on everything that we've learned in the RNN module of this class. The goal estimate is represented as r comma theta, which is embedded with fully connected layers. And then ultimately what we're producing are actions, forward, stop, and so on. But we're going to train all of these parameters through policy gradients, which is what Joanne will talk about next, which is, of course, building on everything that we've learned in our reinforcement learning model. So really all components of what you've been doing come together here. And once we write down our objective function of and how to derive policy gradients, the rest is, computing that gradient via backprop, SGD, and everything that we've done in this class. So go ahead, Joanne.
Yep. So how do we actually train this agent? So both the actions, so they're discrete actions, and the simulator are non-differentiable. And so we'll use reinforcement learning to train this agent. And so the rest of this lecture will follow this outline. So I'll first go over policy gradient methods such as advantage actor critic, TRPO, and PPO. And then finally, in the last half, I'll talk about some applications of this to real-world robots. So let's begin with policy gradient methods. So advantage actor critic, I'll first introduce some notation. So given a policy pi theta, this is a neural network that takes in observations or states from the environment as input, and it outputs an action for the agent to take. And so this action is sampled from an action distribution that is parameterized by the policy. Next is the advantage function, which was also briefly introduced in the last lecture. But to recap, the advantage function is the estimate of the relative value of a selected action. And again, it's shown here simply as a difference between the Q function at a given state and action and the value at a given state. And so the Q function gives you the discounted sum of rewards that the agent got, and the value function is a baseline estimate for how good a state is. So essentially, the advantage function tells you how much better an action is than the expected reward at a given state. And so if the advantage function is positive, that means the action you took was better than what you expected. And if the advantage function is negative, that means that the action you took was worse than expected. And so in the last lecture, we ended off by showing the formula for advantage actor critic, which is the log probability multiplied by this advantage function. And this might seem intuitive, since if the advantage is positive, then you want to increase the probability of selecting those same actions again in the future. And on the other hand, if it's negative, then you want to decrease the probability of selecting the actions. But can anyone see what might be the problem with this? And again, I can't see the chat, so Drew, just let me know if there are responses.
Sure. So the question for you is, where might this go wrong? What might there be problems in training this? And the task that we're trying to solve here is point call navigation. You have a robot that's spawned somewhere. It's asked to go to a particular point. You can imagine that if your reward was sparse, that you only got +1, -1 reward for reaching a goal, then the value function is roughly telling you how far you are from the goal, how far a particular state is. And a Q function is telling you a particular action. Is it taking you closer to the goal, or and the advantage being positive is telling you that you're getting closer to it. And so the question on the table is thoughts. How might this go wrong? What might be the problem with A2C objective here? We have no responses so far. Joanne, do you want to give them a hint?
So I guess, is there a certain magnitude that you would update? Is there a problem with updating a policy too much?
We still don't have any responses. It's the hard one. Why don't you go ahead?
Yeah, so the problem with this is that if you perform multiple steps of optimization using the same batch of data, you might end up optimizing your network too far out of the range from where this data was originally collected, and this could lead to a destructively large policy update. So that means that your policy might become very poor with this update, and this in turn affects the next batch of data that gets collected, and then your policy might not be able to recover from this. So essentially, if you update your weights too much and you go too far away from where your previous policy was, you might end up in a state where you can't recover anymore.
Joanne, we do have a couple of responses that have come in. One response is that good actions in the past might not be good actions in the future, which I think is getting to what you're saying, that if you might, it is possible to overfit to a good action, right? And so can you, I guess your response of you can have too much updates happen to your policy. Can you make that a bit more concrete in terms of the point goal navigation example? So let's say there's an action. I'm at a particular state, like there's a robot that's standing in the middle of the room. It decides to move forward, and that moving forward does actually take it closer to the goal. So the advantage function is positive. How might that forward action be overfitted in this case?
Yeah, so if the agent believes that taking a forward action is really good and it wants to increase the probability of choosing the forward action again, it might just always want to go forward. That would cause the robot to end up colliding against obstacles, and then it would never be able to reach the goal if it doesn't know that it has to turn to get into a room and then call forward. So it might overfit to that singular forward action.
Correct. So I guess the concern here is if looking at the objective here, the only thing that seems to matter is you took a forward action and that made you better. So therefore, let's just increase the gradient so that we take forward actions again. If in our initial unrolling of our trajectory, if our initial data set that our robot has captured, it never took turns, then it would just never decide to increase the probability of the turns. And if all it did was move forward, then it would just conclude that moving forward is always the right answer. And so part of the problem here is that the same problem with reinforcement learning, which is you're learning from data that the robot has collected, not that an expert has demonstrated. So if you never exhibited a behavior yourself, you do not learn to replicate that behavior. Okay. There's another question that has come in, Joanne, which is more about the task, less about reinforcement learning. And that question is, are the GPS and compass measurements trustworthy enough that you don't have to worry about localization problem for state estimation, that is to use a particle filter? So there's a follow-up question about that, which is you're assuming that the map you use is good, but actually I think that question has an assumption built in that is wrong. I can clarify that later. So I guess let's take the first part of that question. The GPS and compass measurements in simulation, are they good enough?
Yeah, so the measurements in simulation are actually perfect. So the robot will always be perfectly localized in simulation. The problem is if you want to transfer this to the real world, and I have some examples of this later on in the lecture where I actually did take these policies that were trained in simulation and deployed them on the real world. In the real world, we don't have perfect GPS and compass localization, but we can get pretty close to it using either LiDARs or other tracking cameras in order to get an estimate for where you are. And these estimates are good enough that they can actually transfer well, even though it was trained in simulation where all the estimates were perfect. And there is also follow-up work where we sort of remove this reliance on a perfect GPS and compass sensor. And that's work done by others in my lab. So you can either use visual odometry or other methods to sort of estimate this and learn how to track yourself along the way as you're training your policy. And there are other ways to combat this.
Yeah, sounds good. So in short, right now we're assuming the GPS and compass is perfect. If it is not, then we will have to do the kinds of things that this question is saying, which is, use a particle filter or some kind of methods to do state estimation. There was a second part of that question, which is that you are assuming that the map you use is good, and so you don't have to run a mapping algorithm like SLAM. I want to just sort of mention that there's a premise in that question, which is incorrect. Everything that Joanne is showing does not actually use a map. That's one of the hard parts of this problem. If you assume access to a map and you assume access to localization, then this is a purely a graph search or a planning problem. You just write down nodes, you discretize your search space, 2D points on a grid, and you just run A star or some other planning algorithm. You don't have to actually process images because you've assumed mapping and localization to be solved. The hard part here is to do all of this without any map. So you just know relative location, how far the robot has traveled, and you perceive directly to go from pixels to actions. And that's what makes this challenging. Okay, so back to the lecture. Joanne, you've introduced A to C. We can continue from that point.
Yeah, so actually next I'll transition into TRPO, or Trust Region Policy Optimization. And TRPO tries to overcome the problem that we previously saw in Advantage After Critic. So the setup is similar to before, where we have a certain policy pi theta and we have an advantage function. But this time we introduce pi theta bold, which is the policy before it was updated. And so the goal of TRPO is to make sure that we're updating, make sure that when we're updating our current policy pi theta, we don't deviate too far away from our old policy. So essentially, we don't want to update its weights too much to overfit to a certain action. And so to do this, they introduce a surrogate objective function. And the first part of this surrogate objective function is a probability ratio. And this probability ratio tells you how likely an action is with your current policy relative to your old policy for a given state. And so the ratio is a scalar value, and this will be greater than 1 if the action is more probable now with your current policy than it was with your previous policy. And the ratio will be less than 1 if the action is less likely now with your current policy. And in practice, you can store all the information you'll need to calculate this ratio in your rollout. And so the surrogate objective of TRPO is now to maximize the advantage multiplied by this new probability ratio. And if we compare that to the previous objective that we saw, we see that it's very similar. And the only change is that now we're using a ratio instead of the log probability of just your current policy. But there's still one more component left to get to the full objective of TRPO.
Sorry, before you get to that objective, Joanne, I just want to pause here and say this is a recurring theme that you have seen in reinforcement learning, that we go out and gather, the agent goes out and gathers data itself. It wants to update its parameters of whether a queue function or a policy network. And you sort of have this sort of odd nature of things where you want to update your parameters, but not too much. This is not something that happens in supervised learning, because in supervised learning, the data set is what the data generating distribution is not under your control. So you can take as many steps on the data that you want. The only thing that you're concerned about is overfitting. And so you solve that with regularization. In reinforcement learning, you're always sort of partially skeptical about the data, because while you have the data, there are large parts of the state space that are missing from the data that you could get to. And so therefore, there's this balancing act of, I want to make some updates, but not too much. In DQNs, that is why we were maintaining an old queue network and a new queue network. And here we're maintaining an old policy and a new policy, and we're sort of playing that balance again. Okay, go ahead, Jim.
Yeah. So in addition to this probability ratio, the authors also introduced a KL divergence term. And so this KL divergence term basically measures how different the previous policy distribution is from your current policy distribution. And we want to discourage updates that will cause the current policy to be too different from the old policy. And so if we combine both of these, we'll get the full objective of TRPO, which is just the subtraction of these two terms. So it's the advantage times the probability ratio minus beta times KL, the KL penalty. So while this is great and it overcomes the previous problem that we saw where the policy might be updated too far in one direction, a disadvantage of this approach is that now you have to compute this beta KL term, and this adds additional overhead and it makes the learning harder. And also in practice, this beta is pretty hard to tune, and it's difficult to find a beta that would work across multiple different problems. So now I'll transition into PPO. So PPO was developed by folks at OpenAI, and it's been proven to be successful in a wide variety of tasks, ranging from video games such as Dota 2 and StarCraft, to robotics tasks such as locomotion or in-hand manipulation. And in practice, this is the state of art that most researchers use when doing on-policy reinforcement learning. And PPO seeks to overcome the problem introduced by A2C and also the problem in TRPO, where again, the goal is to keep the policy from updating too far away from its previous policy. So we want to be conservative in our updates when we see something that might seem lucrative or advantageous in a certain time step, but at the same time, we want to allow for intense recovery from bad updates. And we also don't want to have to deal with this KL divergence term and also deal with tuning the beta hyperparameter as we did in TRPO. And so to do this, all they do was get rid of the KL divergence term and instead introduce clipping of the surrogate objective. So this clipping term modifies the surrogate objective by clipping the probability ratio to remove the incentive for moving R of theta or RT out of the interval of 1 minus epsilon and 1 plus epsilon. And by taking the minimum or maximum of this clipped objective, we can curb drastic values to the probability ratio when it would make the objective improve, and we would keep it unfeathered when we want to undo the previous gradient step. And I'll illustrate this in some plots. So to visualize this, we'll start with a case where the advantage is greater than 0. And so if we recall, having an advantage greater than 0 means that the action we chose was better than our expected return. And we see that here the objective flattens out in this case when the probability ratio gets too high. And again, the probability ratio is really high when the action is more likely now under the current policy than it was for the old policy. And so in this case, we don't want to update the policy too much. And so that's why we clip it to limit the gradient update.
So can you go back, Joanne? So yeah, I just want to make sure people again can ground this in the context of an actual application like point goal navigation. So state you can assume is some position on the floor plan. Action is move forward, turn left, turn right. Advantage may be positive because you're getting closer to the target. Advantage being positive means you want to send the message back that you do actually do that action again because that's a good thing to do, but you don't want to overfit to that action or just forget about your old policy. And so that ratio R T of theta is telling you, okay, so I want this advantage is positive. If my objective was just advantage times R, then I would update my parameters theta such that I would move strongly in the direction of those parameters that make this action very likely. Now by clipping R theta to a max value, that max value is 1 plus epsilon. Epsilon is a parameter that doesn't really matter that much, but the fact that you clip it means that the gradients going back to the theta update will flatten out to 0 at some point either as well. So this is playing a role of making sure pi theta for this action doesn't continue to just improve as you take steps in the direction of that gradient. So that's the role that clipping is playing. Joanne's shown that on this slide for the positive advantage case. On the next slide, she'll show it for the negative advantage case. But essentially, it's doing the exact same thing. It's just a mirror image of this slide. So if and this slide is not. It can seem fairly mathy, but it's essentially providing a max clipping and a 0 gradient once you go outside of it. Go ahead, Joanne.
Yep. So like Drew said, this is just the mirror image. So if we plot this for the same clipping behavior at 1 minus epsilon, again, this is the case where advantage is less than 0. So the action we chose was worse than the expected return. And this is also in the region where the probability ratio is less than 1. So that means the action is much more unlikely under the current policy than for the old policy. And here we similarly want to clip this behavior so that we don't decrease the probability of this action too much. And so what happens in the ranges where it's not being clipped? So this objective only ends up in this region for the last time step if, again, the advantage is less than 0, but in this region, the probability ratio is greater than 1. So that means that the last gradient step made the action much more probable, so R is large, but it ended up making our policy worse, so the advantage is negative. And in this case, we want to sort of undo the last gradient step, and the objective function in PPO allows us to do this. So here we're allowing for intense recoveries for bad gradient updates in our previous policy. And so the advantage of PPO is that we're able to perform multiple optimization steps per rollout. In most cases, epsilon equals 0.2 sort of works in lots of cases, so we don't need to really tune this parameter too much, and we can easily handle networks with hundreds of millions of parameters. But one disadvantage to this is that other methods might be more sample efficient. So for an example, off-policy algorithms might be more sample efficient than this.
Is sample efficiency means how quickly you reach a particular reward value or a particular objective or a performance as a function of amounts of the number of actions or steps taken in the environment. So sample efficiency is of high concern in reinforcement learning when it is applied to realistic systems in the world like robotics, because the more number of interactions that you have in the real world, the more likely it is that you will just never make it out alive, like the robot will break or something else bad, catastrophic will happen. Sample efficiency is not that important if all you're going to do is deal with software systems, because with bounded consequences. So for example, in simulation, it's perhaps not all that critical to be highly sample efficient. You still want some amount of sample efficiency because otherwise you'll just run out of time and compute or other such budget requirements. But it becomes really critical once you're dealing with physical systems. Go ahead, John.
Yep. And in practice, the implementation of PPO is you would collect a set of trajectories using your current policy, and for a few epochs, you would sample mini batches from this rollout. And then you would use that to update the policy using a step of the PPO objective that we've just shown, and then you would just repeat this. So now I'll transition into the last part of the lecture, which is applications to real-world robots. So I'll start with point goal navigation and also talking about sim-to-real transfer. So again, the task of point goal navigation, the agent is spawned in an environment and it has to navigate to a goal location without access to a map. And so prior works have shown that learning-based approaches can reach a really good performance for the task of point goal navigation in a validation split. So these are unseen scenes for the robot. And the metric that we're using here, SPL, is success weighted by path length. So if this effectively measures the efficiency of the robot. So we want the robot to take the most efficient or the shortest path to the goal. And prior works have shown that training the robot out to 100 million steps, you're able to get 0.86 SPL, which is relatively high. But what we want to see is what would happen if we were to scale this out. So if we're able to scale our learning algorithm, how much would the performance improve by? And so this is work done by someone else in my lab, Eric Wymans. And so he developed a method called Decentralized Distributed Proximal Policy Optimization, or DDPPO for short, that looks at scaling these algorithms and seeing how far we can improve the learning performance. So if we were to continue training this, more so than 100 million steps, if we train it out for 2.5 billion steps of experience, we see that the agent continues to learn, and it reaches an SPL of 0.95. So essentially solving this task where the agent can navigate near perfectly in previously unseen environments. So this was, again, 2.5 billion steps of experience. This is trained with 64 GPUs. This is around 6 months of GPU training time, but this was all done in under 3 days of wall clock time.
So just to make sure, just to make sure people absorb those numbers in context. So in your homework, you're doing updates of, I think, 50,000 steps of update. So somewhere in the order of tens of thousands of updates. This plot started at a few 100 million, and it's going out to 2.5 billion. So we've covered from 1,000 to million to billion. So there's like 6 orders of magnitude of difference between those. The other thing is that if you actually calculate the amount of real world experience, so if these experiments were done on a real robot, how long would it take for that real robot to be navigating out in the wild? I think based on some approximations of how long it takes a robot to move forward versus how long it takes this particular robot to turn in place, some back of the envelope calculation suggests that it's 2.5 billion steps of experience corresponds to something like 80 years of running that robot. So 24/7, just keep running that robot in the real world. Let it take actions. That would correspond to 80 years of experience. And so this really is the reason to go with simulation. They let you scale methods in a way that would not scale in the real world. Now, the common question or the common concern around at this point is typically, okay, it works in simulation, but does that ever translate to real robots? And that's something that Joanne will talk about in future slides. Joanne, we also have a, sorry, go ahead.
Oh, no, if you can go ahead.
There was a question that came in. Have people tried using a momentum term while updating the policy? So instead of using a KL divergence term to keep it close to the previous policy or the clipping, have people tried using a momentum term for the policy?
I'm not too sure about that, Drew. Do you mind taking this question?
Yeah, no, I can take it. Nothing immediately comes to mind. It's a good idea. I've seen most of these momentum things I've seen in the context of self-supervised learning. So encoders for images where the parameters of those encoders are updated with a momentum term. Meaning that you take 1 minus gamma times the old parameters plus gamma times the new parameters, where gamma is set to some small value like 0.05 or 0.01. That's what, for people who don't know, that's what that momentum term means, and this is something that Ishan and others talked about in the self-supervised thing. I have not yet seen momentum applied to policy networks. If you recall, in DQNs, we did see an idea of momentum, right? Because when you maintain old setting of parameters for the Q network and you're updating the old setting to be the new setting after some number of iterations, that is a very odd form of momentum. And I'm fairly certain I've seen works where they've replaced that with the average of the last few parameters, last few iterations. I have not yet seen that in policy gradient methods. I suspect the reason why we haven't seen that is that so PPO just performs better than TRPO, and it performs well enough that that's not the place where people are struggling now. Yeah, but we can look into this and get back to you. No, nothing immediately comes to mind. Go ahead, Joanne.
Yeah, so first, let's look at some qualitative results from the policy that was trained for 2.5 billion steps of experience. So here, the robot is trying to navigate to the red position marked in the top-down map. And at this point, it can go in 3 directions. It can go straight, or it can turn left, or it can turn right. The GPS and compass is telling it that the goal is directly in front of it in a straight line. But what the robot notices is that straight in front of it is a wall or a bookshelf, and to the left of it is a door. And so in this case, the robot decides to turn right, which is the correct action to take at that point. And then it can, from there, successfully reach the goal.
I want to temper that language a bit. Although Joanne mentioned that the robot decides to do X, or the robot notices Y, I want to temper that language a bit. We don't know why certain decisions were taken. It is a common trap to fall into when training neural networks or any machine learning systems to anthropomorphize them. All we can say is that it is likely that those 3 options could have been taken at those points. Those were in the action space. It is interesting to note that no exploration was done, that no left or right turns were taken there. And so this is an exhibition of intelligent behavior, but we don't know. And as far as we've seen, we have not seen any sort of obviously wrong mistakes being made, but we don't know whether there was an explicit attention mechanism that we could read into to see whether it actually did notice, quote unquote, or the obstacle in front of it. Go ahead, Joanne.
Yeah, and one more example of this intelligence is in backtracking. So here the agent wants to reach the point on the red point, and it's supposed to turn into this bedroom, but instead it continues straight. And so at this point it notices, or yeah, I'm assuming it notices a door, and so it can't actually make this turn to get to the goal anymore. And so this agent has learned a backtracking behavior where it can actually trace its actions back. Here it realizes it made the wrong turn previously, and now it can go into the room and reach the goal successfully. So these are just some interesting behaviors that we've seen that the agent has picked up on after being trained out for so long. And so my research was focused on sort of deploying these on real robots. And so the question I was trying to answer was, does progress in simulation translate to progress on real robots? So if one method outperforms another in simulation, will it continue to do so when deployed on a robot in the real world? And so this is important to ask, as a lot of research has been focused on developing simulators, and embodied AI challenges have been proposed. How can we actually trust that the results and outcomes from these challenges in simulation will also hold true in the real world? So this is this is the scanning process that we had previously mentioned when we were looking at the Habitat Sim demo. So here what I was doing is placing a 3D camera at multiple points in this real world environment that we had to collect 360 scans. And these scans can be used to reconstruct highly realistic 3D meshes of the environment. And the 3D meshes can be directly imported into the simulator to allow us to virtualize physical spaces quickly. And so with this, now we have paired worlds. So I have the real world lab environment. This is building a room in Coda. And we also have a virtualized replica of the environment in simulation. We also have the same robots in both environments. And so now we can run paired experiments. So we can run identical experiments using the same models in both simulation and the real world to see how the performance is different between the two. And the evaluation environment, again, is the room in Coda. The robot has never seen this room before during training, and we create different room configurations with a different number of obstacles, and the robot would have to navigate through these waypoints sequentially, so from A to B to C and so on. After every episode, the robot is automatically reset and has no knowledge from its previous run. And to automate this process a bit more, when the robot is unsuccessful, the robot uses a pre-built environment map to navigate to the next episode start position, and then it would continue running. And this is just to reduce the burden of me, the human supervisor. So using this pipeline, we conducted a total of 810 identical experiments in simulation and reality. And the reality experiments took over 40.5 hours to conduct. And what these experiments allowed us to do was to run these models in the real world and freeze the results of the reality experiments. And from there, we can just experiment more in simulation, change the parameters of the simulation, and tune these parameters such as noise to better understand the notion of predictivity. So how well does simulation predict real-world performance? And we can quantify the degree of predictivity between performance in simulation and reality using a new metric that we proposed called Sim versus Real Correlation, or SRCC. And here the x-axis represents the robot's performance in simulation. The y-axis represents the robot's performance in reality. And these points are 9 different learning-based navigation methods that we tested. And SRCC is calculated as the sample Pearson correlation across data points. And what we want to see is an SRCC value close to 1, or have the points along the diagonal of the line, as that would indicate a high linear correlation between performance in simulation and reality. And by plotting the performance in reality against performance in simulation as a scatter plot, we can reveal the existence of performance correlation and detect outlier simulation settings or evaluation scenarios. And And so these, the SRCC from the original 2019 AI Habitat Challenge was 0.18, which meant that the results in winners may not be the same if they were run in the real world. But if we were to search over the various simulation parameters and optimize for SRCC, now we can see a better alignment between performance in simulation and reality. And overall, this gives us a formal approach to simulator design instead of operating on intuitions and qualitative assessments. And from these results, subsequent challenges proposed in the Embodied AI workshop at CVPR 2020 and 2021 have focused on realism and sim-to-real predictivity by disabling something called sliding, adding realistic sensor noises, and also by directly evaluating robot policies in the real world. So here is also another video. This is the same agent from the one in the green room, but this is just evaluated in a more cluttered environment. So this is the lobby of CODA on the 11th floor, and it's able to reach the goal position that I've specified. And following subsequent work done by another lab mate, Naoki Yokoyama, is to leverage the local bot's dynamics. So while the robot that I trained was trained using discrete actions, his work was interested in how to leverage the robots, the dynamics that real world robots would have. So for an example, real robots like Locobot, Fetch, Returnabot, they can move and turn simultaneously, and this is called Unicycle cart dynamics. And so if you look at the figure on the left, while a point turn robot can only pivot or move at a given time, the unicycle robot can also do curves, which is very natural for robots to do. And so here is a visualization of what that might look like. And so the unicycle agent can actually navigate faster than the point turn robot, even though both of them have identical maximum velocity limits. And this is an example of running the robot in a real world apartment. On the left, we have the Unicycle 6 agent, and on the right, we have the point turn robot. The robot is initialized in the apartment here, and it has to navigate to the goal here. And so if we were to run these both simultaneously, we'll see that the Unicycle 6 agent is able to reach the goal much faster than the robot with point turn dynamics.
Joanne?
Yeah.
This might be a good point to ask a question that has come up. There's a question on how do you account for robot tolerances, that is, to avoid collision. So, for example, the radius of the base is 100 centimeter, and that the robot should avoid getting close to the walls by a factor less than 100 centimeters. So how is that? How is sort of collision tolerances avoided handled in this?
So specifically in Habitat, one way that they're able to make the simulator really fast is by doing a lot of physics approximations. And so what that means is that the floor is approximated using something called a navigation mesh. And so these are just a collection of polygons on the surface, and the robot is sort of transported to these the edges of these polygons at every given point instead of actually having to calculate the physics at every step. And so what we can do is if we have like a map of the environment, we can sort of add a buffer or add a threshold to this. So we inflate all the obstacles by a certain radius. And so those become regions that the robot can't navigate to. So if we know the radius of the Locobot agent, we can inflate all the objects by that. And so it won't be able to reach those locations during training time.
Yeah, so that makes sense, and that's where a robot can go in simulation and where it can't. But I imagine that this question was also trying to get to what if, as a human designer, I'm trying to encode a preference that the robot not get too close to obstacles. So while it is possible for it to get closer, I just wanted to stay a little bit far away from obstacles. How do I encode that preference? Is through reinforcement learning, right? Because if this was a mapping plus planning algorithm, I would put this into my planner such that anytime it got closer by a certain factor, I would have a negative penalty or a cost associated with that location. How do I do that in reinforcement learning?
Yeah, you could also add another reward term in that case. So you can have an additional sensor on the robot that tells you how close it is to obstacles nearby. And if it's too close to an obstacle, then you can add a penalty to the robot, and then that would encourage the robot to stay a safe distance away from obstacles.
Yep. Exactly. So the answer is that your reward functions are fairly expressive. If as a sort of system designer you have certain preferences that you can put into the reward function. I do want to at this point acknowledge that this is a common problem in reinforcement learning. That tuning the reward function to get the desired behavior can be a fairly challenging and complicated task. To the point that it has a derogatory name, it's called reward engineering, which is that human designers will sit down and say, okay, like if I want you to get to the goal, writing that part is pretty easy. But how do I express that don't get close to obstacles? Well, I have to keep track. Are you getting close? Then I'll penalize you by some constant factor or some distance to an obstacle. If I want to express that, move sufficiently quickly but not too fast, then I have to put in another term. If I have to put in a preference that don't move in a jerky manner, meaning that don't have sharp accelerations or stops and goes, then I have to put in another term that penalizes for that. So ultimately, these things get to large number of components of the reward function that each have individual multipliers on them, and you're sitting there tweaking them for each choice of those hyperparameters. You have to run this expensive reinforcement learning inner loop to see what sort of policies are learned. Then a human looks at what behavior is being exhibited, and then has to make updates to that. So that is a known problem. There is a branch of reinforcement learning or sequence modeling or learning to act, which is known as inverse reinforcement learning, where you see demonstrations from an expert and that expert is already acting in a manner that they want the agent to act in. So if they don't want to get close to obstacles or if they don't want to have jerky behavior, that is visible in the demonstrations. And what you want to infer from those demonstrations is what reward function were they optimizing. So it's inverse reinforcement learning because you want to infer rewards from behavior rather than behavior from rewards, which is what reinforcement learning typically does. That is outside the scope of this class because this is not a full-on reinforcement learning class. I encourage you to take classes by Sehun Ha, Matthew Gompole, who sort of go into those topics. I think from a deep learning perspective, a lot of the tools will be the same. You'll write down some inverse reinforcement learning objective. You'll sort of look at function fitting approximations within various pieces. You can approximate the policy, you can approximate the inverse function, you can approximate the forward function, and you will fit in neural networks in between those cases. Okay, go ahead, Jim.
Yeah, so now I'll transition into the last portion of this talk or lecture. So this is robot-to-robot transfer, and this is work that I've been doing recently. And so I was interested in looking at being able to train policies for multiple different legged robots. So legged robots are well suited for navigating indoor environments, and legged robots such as quadrupeds from Unitree, Boston Dynamics, and hexapods from Heavy Robotics. They've all emerged on the market as mature, robust commercial robotic platforms. And legged robots are agile and they can easily traverse uneven grounds in homes like carpets and stairs. And so they're sort of ideal for indoor navigation. And in addition, for robots to effectively assist humans in complex real-world environments, it's important to develop a variety of robots with different sizes and functionalities, as different robots might be better suited for different environments. So for an example, mobile-based robots are useful for navigating across factory floors, quadrupeds are useful for rough terrain, and hexapods are capable of changing its shape to fit through long and narrow pathways or low and wide clearances. So this raises the question, how can we learn a single navigation policy for multiple complex legged robots, such as A1, Alien Go, or Daisy that may be of different sizes, masses, or number of legs? And how can we sample efficiently generalize these learned policies to new previously unseen robots? So such as Lycago, which is a large quadruped, or four-legged Daisy. And while recent works have investigated teaching robots to learn using reinforcement learning, many of these works either navigate without any visual input, or they navigate using expensive LiDAR sensors to map the terrain and use it to select footstep locations. So in our work, we're interested in indoor navigation, where the robot has to navigate around obstacles, go through narrow hallways, all using RGB and depth cameras and localization sensors, so without using a LiDAR or a map of the environment. So in our work, we investigate this again for the task of point goal navigation. So while a spherical agent can successfully navigate to the goal using a point nav policy, if we were to take that same policy and deploy it onto Daisy, the hexapod, we'll see that the robot actually gets stuck around an obstacle due to its larger size and turning radius. And so the dynamics differences between these robots were not accounted for by the policy, which led to this failure. And furthermore, we see that if we train a policy directly on Daisy, then Daisy is able to successfully navigate to the goal. But again, if we transfer that same policy onto a new robot, the Alien Go, this results in Alien Go drifting, and thus it fails to reach the goal within the maximum number of steps allowed. And this example highlights the importance of incorporating robot-specific dynamics when learning navigation policies for legged robots, and the challenges of generalizing such learned policies to new robots. So to combat these issues, in my work, we investigated using hierarchical visual navigation policies. And so our approach consists of three components. The first one is a hierarchical navigation policy. So we divide the control of the robot into a high-level policy that reasons about the center of mass motion, and a low-level policy that converts these high-level linear and angular velocity commands into desired footsteps for the robot to take using an expert-designed feedback policy. So the footstep planner is shared across all 5 robots that we have, which allowed us to experiment with multiple different robot designs. The second part of this is that we learn a universal navigation policy across multiple robots. So here we're actually using soft actor critic, which we didn't introduce yet, but this is the off policy algorithm that we decided to go with. And so the actor and critic are shared across all of our robots. The policy takes in as input an egocentric camera image, the goal coordinates specified in the robot's reference frame, and also a learned robot-specific embedding, which we denote as Z, which the policy uses to adapt to different morphologies. So first, a learned scalar is initialized and is fed into an encoder that we call a Z network, and the Z network is a feed-forward network that outputs a robot-specific embedding. And so both the inputs Zin and the parameters of the Z network are learned alongside the shared policy. And finally, the output of the policy is a 2-dimensional vector containing the desired center of mass, linear and angular velocities for the robot to follow. And another key component of our approach is that we share data across the robots during training to sample efficiently learn a navigation policy. So at the start of training, each robot is initialized in a different environment and tasked with navigating to different goal locations. At every step, each robot adds to its individual replay buffer, which is just a collection of state and action pairs that the robot has taken. And the replay buffers are combined and shared across the multiple robots. The shared replay buffer is used to jointly update the shared policy between the robots, but the individual replay buffers are used for updating each robot-specific embedding. And by collecting data across multiple robots and environments for training our policy, we can train sample-efficient policies, and the resulting universal navigation policy will be robust to the differences in the robot dynamics and environments. So at test time, our navigation policies can be adapted to new robots by searching for the optimal robot embedding, and the learned embedding captures different dynamical properties of each robot, such as turning radius and walking speed, which results in different center of mass trajectories. And our approach also shows promising results on robots that it was never seen before. So there was 4-legged Daisy, and it was able to reach the goal in a relatively straight path. And to demonstrate this, that our policy is able to successfully navigate, we use 5 different legged robots in simulation and 1 real-world quadruped. So specifically, we show results on the 3 robots it was trained on, evaluated in new environments, and also 2 previously unseen robots in simulation and 1 real-world quadruped, and it's all in new environments. So here are some video results. Again, the robot only has access to egocentric RGB image, egocentric depth, and again, this top-down view is only used for visualization and is not available to the robot. And so here is A1, which is one of the robots it was trained on, navigating in a new environment, and it has to back out of this bathroom in order to reach the goal. Here's another video of Alien Go. So again, one of the robots it was trained on, evaluated in a new environment. Next is Daisy, and we see Daisy making its way around a couch to reach the goal. So in new environments, the robots still collide with obstacles, but they're able to recover and successfully navigate to the goal. And this is an example of Lycago, which is a robot that was unseen during training, evaluated in a new environment. And again, these robots are all using the same policy, so it's just one single policy that's able to work on all these different combinations of robots. And the last robot in simulation, four-legged Daisy. And next, I have a couple videos of the A1 robot in the real world. So this is a real world apartment that it's never seen before. And we show zero-shot sim-to-real generalization of A1 robot. So this robot was trained purely in simulation, and we directly deploy this onto the real world without fine-tuning or looking for a new Z embedding. And so the robot only uses an RGBD camera to reason about the environment and avoid obstacles in its path. And we show that A1 is able to avoid obstacles and navigate through narrow hallways in the real world to reach the user-defined goal positions. So that was the end of the lecture. Thank you, and I'll be here if you have any questions.
Thank you, Joanne. We have one question that has been waiting that came in earlier. I'll read that out and we can go over that question, but we encourage you to ask other questions in the Q&A tool. So the question is, Joanne, what are the benefits of RL compared to traditional SLAM in navigation problems? And I suspect what they really mean is the sense, plan, act, like the mapping, localization, and then planning pipeline. Why might I want to use reinforcement learning here?
Yeah, so so there are multiple ways to answer this question. One, yes, traditional classical approaches can be incorporated within these learning pipelines, but the benefit of using reinforcement learning is just that the agents can learn to achieve a much higher performance than traditional approaches. So traditional approaches, you map the environment, which means that first you would have to have access to the real world environment and create this map before the robot can navigate in it. Whereas in reinforcement learning, it's learning from in simulation on other houses, and then you can deploy it into a new environment without having to do this pre-mapping stage. And if you want to check out the Habitat paper from ICCV in 2019, they show that these learning methods are able to outperform traditional methods, which sort of stay constant with the amount of data that you give it because it doesn't use data, versus using reinforcement learning works as the data increases, the performance of your policy can continue to increase and the policy can continue to learn over time.
Yep, and if I can add a little bit more perspective to that, I think this comes down to something that we discussed in the first lecture of deep learning, that by and large, in a number of fields, computer vision, NLP, robotics, you come across pipeline systems. Pipeline systems have modules in them. Like if you want to build a system for image captioning, which was the example that we gave you in the first lecture, a pipeline system would first take an image, run an object detector, come up with a set of nouns and verbs that have been detected in that. Then a next module would take over composing those nouns and verbs into sentence candidates and produce multiple of them. Then the next module might rank them. In a navigation problem, those pipelines, it's still a pipeline. The modules are different. You have, first an incremental mapping module or a SLAM module, which is doing simultaneous localization and mapping. Then a second path planning module. Then a low-level controller that is taking actions coming from a planner and actually executing them on the robot. The problem with pipeline systems is that anytime you make a mistake early on in the pipeline, errors cascade and things turn catastrophic very quickly. Those are brittle systems because the errors cascade, the successes don't. And so you're always dealing with, in some sense, the problem of having numbers less than 1 multiply themselves. So the success rates for each stage in the pipeline are going to be less than 100. Multiply enough of them and you will get compounding errors. That's the problem you're dealing with. what deep learning or the idea of differentiable programming brings to the table is to update early parts of the pipeline by looking at downstream performance, to fine tune them to based on downstream performance. It's not a panacea. It does not mean that long pipelines or long deep networks will suddenly do better. It just means that you can adapt to the failures that are happening downstream in the pipeline. And so the analog of image captioning was, take a CNN, take an RNN, produce words one at a time, directly go from pixels to words. The analog here in navigation is directly go from sequence of pixels to sequence of action. And ultimately, as we've discussed in a number of these different domains, what is much more likely to happen is that domain expertise is valuable. What we've been seeing in the research communities is that people who initially, the first set of methods are domain agnostic. You just take generic components, CNN, LSTMs, and transformers and try to produce the output. Then domain experts realize that it is better to make each part of the network specialized to certain tasks. Maybe there's differentiable mapping, maybe there's differentiable planning. You can do that, then you can piece together differentiable components where you can still backprop through the whole thing, but it's sort of task-informed architecture design. And so we've all sort of converted from building modules to building differentiable modules. And there was an answer in the chat that generalization in short, the generalization and lack of cascading errors. Okay, there's another question that has come in, Joanne, which is there a GitHub repository for any of these projects? Like, where can people go to learn more about the actual code?
You can go to the Habitat Lab GitHub repo or Habitat Sim.
And they can Google for AI Habitat. You can find those. What about some of the stuff that you showed with real robots? Like that one's, I suppose, harder to get access to without the robot.
Yeah. In that case, shoot me an email and I will see.
Sounds good. That's part of the point of these presentations. If there's a specific area of research that you're interested in, now you know whose domain expertise it is and who to go talk to. Okay, we don't have any new questions that have come in. We'll give it another 30 seconds while we wait in case someone's typing now. But if not, we will stop here. And hopefully this presentation also sets some of the context for homework 5, because you are implementing, you're working with the simulator, running in a Colab notebook, you're controlling the arm of a robot. Hopefully that gives you some sense of working with simulators, implementing RL, working with these algorithms. Okay, we don't have any questions that have come in, so we'll stop here. Thank you, folks.